Hi everyone, my name is Antoine, and I'm a PhD student at the University of Illinois with Professor Praveen Kumar. And today I will talk to you about not cloud-native geo apps. I'm going to talk to you about Agentic LLM for adaptive decision discourse, but I'll make a connection to what is happening here. My work, basically, this is this, so I'll run you through it. What we do is we try to bring pathway of resolution to decision-making problems using agentic LLM assemblies. So that's my agents, like in the middle. And what we do is we submit them with a decision-making problem, and we make them talk about it until some form of resolution is achieved. So what we do is we attribute this agent some stakeholder and some decision-maker persona, so that we can simulate real-life human decision-making contexts. And then we will summarize or create a hypothetical scenario from which we want to draw conclusions. So in this case, we run a disaster recovery or disaster handling situation. Once all that is set up, we run the framework and we make those agents talk to each other so that they can create resolution pathways. We embed certain mechanics in that agentic workshop, which is, for instance, agent summoning. We create this mechanism by allowing the agents to summon other agents with other stakeholder profiles or other expert profiles whenever there is some expertise that's not represented in the assembly. For instance, in this case, if this is about a flawed problem, but all the agents are, I don't know, in another domain, they can actually reach out and say, okay, we don't know anything about flood. Can we have another agent in there? And we can just spawn another agent and add this one to the assembly. So we run all those agents, they talk and they talk. They create a discussion, and once we reach a satisfactory outcome, we batch multiple discussion generations into some sort of a decision tree where we analyze what course of action will greatly or negatively impact resilience pertaining to our problem. So I wanted to give like an overview of what we do, but we'll get back to this because now I'm going to try to introduce a bit why are we doing this. A lot of people here are scientists in some way. What we try to do is understand what's around us. That goes from understanding cause and effect relationships around what we observe. And by making those observations, we can understand what's around. What's the point of understanding what's around us is to be able to ask questions, to predict what could happen, to imagine other scenarios. And those other scenarios can be defined as counterfactuals. Those are extremely relevant in climate change because, as we can see with the LA fires or multiple disasters across the world, there are some events that we've never seen before of an unprecedented amplitude. So we want to ask those questions to get some answers about how we can prevent this, how we can address those situations. Up until now, the champion for this is process-based modeling. What we've done since a long time is we make observations in nature around us, and we build theories from those observations on how those causes will produce those effects, how everything works. Once we have that theory built, we make a mathematical model out of it, and then we validate it and we calibrate it using another observation. And then we have our model. And what can we do with that model? Then we can ask new questions. We can imagine other scenarios and try to figure out what we can do with this. Now the only problem with this, and generally, is that this limit in understanding is the limit in our ability to understand the relationships we model through this process-based simulation model, and also how much observations we have and what conclusions can we draw from this. Models can change if you observe like more and more violent events happening in the world all the time. Those models evolve. Now, since some time, we have another way of trying to understand what's around us using generative AI. So I'm not going to introduce ChatGPT to anyone because I'm pretty sure everyone knows what it is. But the way it works is it's built from a vast amount of data, human knowledge, that's all compressed into a neural network. And the interesting perspective to see here is that that function that's compressed in that neural network is an approximation of human reasoning using natural language. And that's why LLMs are so great at understanding what we say in natural language. You can ask very simple questions and get very simple answers. So, and all those are based on observations because you can see LLM reasoning as a form of deductive reasoning. Basically, its observations will be validated or invalidated, and eventually you'll reach a conclusion to your question. This is deductive reasoning, inductive reasoning, sorry. So the strength of those LLM reside in their generative capacity in natural language and the ability to verify information based on evidence. Now, they don't come without limitations. You might have heard about a lot of them: hallucination, false premises, which is our problem with deductive reasoning, because if the premises in the first place are wrong, well, the logical reasoning is going to be wrong. There are recent material research that proves that LLM are actually better validators than they are quality generators in the first place. So our usage of LLM might be shifted according to that. But what I want to try to say with this is still a recent technology, has a lot of limitations, but eventually we'll focus on what's good with generative AI, and which is their ability to replicate human-like behavior. And now it's not a surprise, decision-making is strongly underrepresented in complex decision-making contexts. You can read this in IPCC reports, National Climate Assessment. We have a ton of people working on a lot of different models to represent the nature around us. However, decision-making is a bit more complicated because mathematically representing human thinking and making decisions is a bit more complicated. But we have collaborative and adversarial agent interactions that can help mitigate a bit of those limitations and help us build decision frameworks with which we can build some recommendations to how to solve problems. And in that context, the example we use to drive our framework is a very simple potential flooding scenario. So we set ourselves in a US Midwestern township, Champaign, for instance, 500,000 inhabitants, and we say, yeah, there's a large river, there's a large watershed, all that. There's forecasts for heavy rain and possibility of flooding at large scale, and consider that the probability of flooding is a certain amount of percent. You'll see later that we run this scenario for 50, 75, and 90%. And we ask that assembly of agents to make anticipated decisions, taking into account multiple optimization constraints. We've got to take care of the population, infrastructure, power delivery, power consumption, all that. And the initial assembly we start the framework with is composed of a mayor responsible for the crisis handling in general, the population. We have a community advocate that tries to ensure that everyone in the community is treated equally, low-income neighborhoods, at-risk communities, and all that. And we also have an environmental science expert that is here to provide valuable information for solving the crisis pertaining to the science part. Additionally, we have a moderator agent that aims to, moderate the debate and make sure that the point is achieved during that conversation, that we're not straying too far, and also that we keep making progress, so exploring new alternatives and all that. And eventually we run that framework, and this is a very short snippet of what's produced. So I'll give you like 10 seconds or so to skim through this very quickly. But in this example, top message is generated by the scientist agent, the mayor answers, and we can see this is a demonstration of the summoning mechanism where we figured out from this message, so there's an LLM agent that pre-processes, that post-processes this, and figures out that we actually need a disaster evaluator. So that's how it works. And when we batch multiple generated conversations, so in this case, we ran the framework 15 times for every scenario, so 50, 75, and 90% chance. And then we batch the answers this way. What we do is, on the left, during discussion, we will just count the occurrence of potential resolution. And on the right side, it's the same graph, but only in the last summary message, which is basically what the agents deemed as like one of the good solutions to keep during the discourse. And so we count all that, and we do a frequency plot. So it's not perfect, and at least it serves the purpose of giving something to look at, because evaluating LLM text and textual response is still a very active research problem. If you have answers, I'd be happy to. What we can see from this is, the point is here is not really to deep dive into those results. And our point is not to have exact, precise answers to give. It's more of evaluating the explorative capacity of this framework to evaluate different options depending on the input framework. And what we can get from this very quickly is that we better capture urgency in the scenario that show a higher probability parameter. And at the same time, flood mitigation reactiveness is better captured by scenarios that show a lower probability parameter. So socially speaking, what's interesting in that framework with those agents is that we see, if we say it's a 50% chance, I guess the actions will be more proactive into flood barriers and communication and all that. However, if the risks get real, that LLM guardrail into not making you take sharp decisions because the LLM is not supposed to kicks in, and then you are more into the communication, evacuation, building aid and relief and all that. So out of now, we can state that some results are representative of a relationship between the given probability and the decision favored. And we use the result to hope that promising evidence of cause and relationship can be established from this framework. As for reliability analysis and confidence and all that, this is something I've just started evaluating. There is very little literature on this, even though it's a very fast-moving, but basically self-confidence analysis for LLM was first published around January or February, so this is still very recent. But what we've done is we've asked the LLMs to self-assess their own answers. So if we take evacuation, for instance, it means that evacuation was listed as like a solution they retain at the end of the conversation. And we asked them for 20 or 30 times to self-assess a confidence score. Like, do you think, based on historical data from what you can recall, is it a good choice? And from that, we can draw another distribution plot. I guess we can generate a lot of things based on those answers. This is just indicative at this point, but what I'm trying to explain here is LLM generate text, and this is still hard to quantify and to qualify how good are those generations, which is why I stress it again. We aim at first exploring a wide breadth of different resolution pathways in the idea of providing support for decision making, not decision making. So now you might ask, okay, well, this is very good, but what we do with it? If we backtrack to the first couple of slides, the point is still the same. We want to ask questions and we want to find answers. And at this point, the only answers I can give is something you might have come up with yourself. What's future for us is we'd like to integrate what we've done, and I'll keep researching that, but we wish to integrate with like some sort of digital twin systems, because what we believe we can contribute to is some sort of a human decision-making digital twin, which is one part that misses from major initiatives. You can read this again in NCA, IPCC panels. So I guess everyone's familiar with what a digital twin is, but I'm still going to repeat it just in case. But a digital twin is a concept that associates a physical system and a virtual counterpart. You can think of a plane, you can think of a NASA shuttle, or the first experiments. And between the virtual and the physical system, you have a bidirectional, or eventually bidirectional data communication real time. Nowadays, digital twins can be smart cities. Well, we're interested in smart cities at least. And this is Destination Earth. It's supposed to be a European Union project that aims to build a digital twin of our planet. What it means in reality is it's some sort of a Google Earth over which you can run all the models that exist with all the data that exists. So at this point, it's still not over, but I guess you can see from what they say here, monitor, understand, simulate, anticipate, it's still the same data flow we wish to understand to ask questions. And what we wish is to be able to integrate with such a framework so that we could test out those recommendation pathways for disaster recovery and disaster address. So in conclusion, LLM offer generative questioning of human reasoning to problem solving. And when you compile those in agentic frameworks, they offer promising improvements over base model on consistency, exploitability, and reasoning. And on the other hand, digital twins offer the ability to ground our generative AI actions using explainable physical models, and we hope that they actually present highly synergistic interactions with agentic LLM frameworks. So, yeah, this is it, and thank you for attending. Any question?
Thank you for the talk. Is it just theory, because it's a PhD, research, etc.? Is there a product or
the QR code is linked to my preprint, and there's the GitHub with all the code in the GitHub. I am actually reworking the code, so like as of now, it's an in-house solution, so like it's pure Python, works, you can run it. But I'm porting it to Google ADK, which is developing most known agentic framework, which is easier to integrate in the future. But there is code, you can run it yourself.
Are you collaborating with other universities or
Not yet, looking for it.
Thank you for your presentation. I think I find it very interesting. I'm not sure if I missed the, how do you, is the training corpus or the base corpus the same for all the agents?
Yeah, so basically all the models we use are off the shelf. So there is no fine tuning, no retraining, nothing.
Okay.
And what we do is we use prompt engineering to reduce their own knowledge space and specialize them in this way.
Yeah, the reason I ask that is, you know, people's decisions may be affected by maybe the knowledge they have, right? Assuming that the human elements like ego, you know, pride or fear are held constant, right? I'm just curious to see if you change the training corpus, how, you know, the decision, I mean, if you provide all the players or decision makers with the same information, maybe that could help us maybe more effective in responding to emergencies or disasters.
First of all, first of all, we're model agnostic. So all this was conducted with GPT, well, at first GPT-4 and now using O1 and O3 Mini.
Yeah.
But I've ran this with downgraded versions of Meta as well and different models using Olama. So because we're model agnostic, if you use another model, the framework will operate differently first. Second, this is very simplified. The actual prompts are way bigger, and the implications are this. The mayor basically says, I don't have any knowledge besides my own political skills and all that. And the point of the environmental science expert is that it's able to bring solutions pertaining to, let's say, hydrology and climatology and stuff, but nothing else. And that's what we try to do, creating the summoning mechanism. Basically, what we try to do is to have collectively exclusive and mutually exclusive sets of knowledge in such a way that if you need more expertise, that will get summoned and added to this. But yes, I mean, to answer your question, yeah, of course, the way the prompt is defined and laid out changes a lot the way this behaves. Yeah. And a big question that we can't yet answer is, are we trying to find the best solutions, or are we trying to replicate a real scenario? Are we trying to be like the real decision-making that happens around us? Or we don't really care about that, but we are more trying to explore. Oh, you see? Thanks.
Hey, thanks. I feel like I might be missing something, but just like, you want to represent the opinions of a community by proxying that community through an LLM. And so what happens when your LLM model says something that the community would not have agreed with? and then like you're saying it's not used for decision making, but like what's the use of it if it's not used for decision? Like there's some really dystopian possible applications of this where you like simulate a town hall and then say like, oh, the LLM that represents you said it was okay to like bulldoze your house, and that's why we did it. Like I don't understand like the use case of this.
In short, the point is to bootstrap any potential conversation that would happen in a non-planned scenario using technology that is fast. So let's say you are a decision maker and something is happening and you know you have to meet in 3 or 6 hours. If you have a booklet of potential explored solutions with like multiple cause and stuff like that, you might be able to do a better job, or at least kickstart from something and not start from zero. To be fair, our use case is not exactly defined yet. Like we don't have any clients or like applications. Also, this we built this because I'm in civil engineering, and this is like my research group's history. We use a disaster recovery event. Technically, this could be used for any sort of decision making. And in the future, we wish to extend to other decision problems. But this is, in the end, those are still exploratory results. So like, this is still the start. It's definitely a question we're asking every day. And yeah, thanks.
Okay, thank you.
Great. Thank you, everyone. Thank you.
So.